Hello and welcome to Let's Talk Stats. I'm Anjali, and in this video, we will demystify ANOVA using a fun example involving dogs. So let's get started. Here's a question for you. Suppose I show you the weights of 45 dogs, all 1 year old. Can you guess what the next dog might weigh? When we don't know much else, we usually fall back on the mean or the median. But looking at how much these weights vary, we can tell that our guess, let's say around 17 kilos, is just a crude guess at best. But what if we had a little more info, like the dog's breed? Suddenly, the picture becomes clearer. We see that German Shepherds are the heaviest, Chihuahuas are tiny, and Beagles sit somewhere in between. The key insight here is that knowing the breed helps explain some of this huge variability in weights that we see on the x axis. So, if I told you the next dog is a German Shepherd, your best guess wouldn't be 17 kilos anymore. It would be closer to the German Shepherd average, right? Which is 30 kilos. Now, let's zoom in a little bit. See these green arrows? They tell us that even within the same breed, the dogs do have some weight differences. Well, that's because not all dogs of the same breed have the same food habits or activity levels. These little differences within each group are called individual differences. But between different breeds, as shown by these orange arrows, the differences are much bigger. And that's why for this particular data set, we can say that breed explains weight differences pretty well. But wait a minute. What if we had another data set like this one, where the breeds aren't so different from each other? For a mix of Australian Shepherds, Border Collies, and Cocker Spaniels, the weights are so similar that the breed-wise averages don't really differ from the overall average. Hence, for this data, knowing the breed doesn't help much. We might as well just report the overall average. Okay, so some breeds weigh very different and some not so much. This brings us to the key question. How different is different enough for breed to matter? And that's the exact kind of question ANOVA was designed to answer. Short for analysis of variance, ANOVA takes the total variability in the weights and splits it into two parts. Between groups variability, which is the part of the variance that is explained by the breed differences, and within groups variability, which captures the individual differences among dogs within the same breed. You remember those green arrows? All right, it's time now to connect the dots. After looking at the two weights data sets, we wanted to know how different is different enough for breed to reliably explain the weight differences among dogs. Well, in the ANOVA framework, this is the same as asking if the between groups variability is significantly bigger than the within groups variability. If the answer is yes, we conclude that breed does explain weight differences, and if it's a no, well, then knowing the breed doesn't help us much. So, is this it? Well, no. We are still missing one key detail. We need to check if the between group variability is significantly bigger than the within groups variability. That is, whether or not the difference is statistically meaningful. And here is how ANOVA does it. ANOVA calculates a test statistic, which is the ratio of between group variance to within group variance. Well, there are a few more details to this formula, as some of you might know, but they are not necessary for a conceptual understanding, which is our main goal in this video. All right, so ANOVA calculates this test statistic, and if it turns out to be large enough, we conclude that the observed differences are not just random noise, but likely due to the grouping. In this example, breed. And that's just hypothesis testing in action. We won't cover the details here, but at the end of this procedure, we get a number called a p-value, which helps us decide whether breed significantly explains weight differences or not. And this is it. If you're with me so far, you have truly understood what ANOVA essentially does. Now, let's step back and summarize. ANOVA is used when we have a categorical predictor such as breed, a continuous outcome such as weight, and we want to see if the variation in the outcome can be explained using the categorical predictor. We start with the null hypothesis that all groups have the same mean. For our dog's example, this would be the assumption that all three breeds have the same average weight. Next, we test this null against the alternative, which is at least two group means are different. And for our example, this would be at least two breeds have different weight averages. We then calculate the test statistic, and if this number is large enough, as indicated by a p-value, we reject the null hypothesis. And that's it. That's ANOVA, one of the most powerful tools in a statistician's toolkit. By the way, we've only been looking at a one-way ANOVA here, where we test the effect of just one categorical variable. But if we had two categorical variables, say breed and diet, we'd use a two-way ANOVA, which is a story for another day. All right, hope you found this video useful. Thank you so much for watching.